Good morning, good afternoon, everyone, to this Texas Instruments webinar, where today we'll talk about a new solution for tomorrow's energy conversion system. And my name is Olivier Monnier, and I will talk today about a new addition to the C2000 microcontroller portfolio. The agenda will describe the following points. So for the people who may be new to this family, we will talk about the landscape of application from the C2000 microcontroller portfolio and position the F28P65X coming with a lot of new exciting features on the analog side, the CPU, PWM, in order to really make power electronics more efficient for the future. And we will also highlight some application examples and how to get started on this device that is sampling today on TIA.com and moving to production for some packages by end of this year. So for if you are not familiar with the C2000 real-time microcontroller portfolio, it's a platform of devices that has been on the market for the past 25 years and really looking at how to optimize energy conversion for power electronics. And we can see two classes of applications, a motor control like motor drive, appliance, and also digital power, like for example, a solar system or charging station or an onboard charger for an electrical car. So the device is supporting both industrial and automotive application, really focusing on optimizing energy for power electronics. So if you look at a typical block diagram, you will find ingredients which are probably familiar to you, like some analog sensing, some processing, some control, communication, and coming with a flash-based solution with implementing as well safety and security. But what makes really the C2000 real-time microcontroller special in the industry is that we focus on minimizing the time between the sensing, the processing, and the control. We make this time as small as possible. We optimize the real-time latency in order to deliver you the best option in terms of energy efficiency and driving a better power density, as we know that in the future, switching frequencies for power supply will increase and will bring new challenges for developers to implement their solution. And in particular, for the adoption of beyond IGBTs, the implementation of technologies like GaN and silicon carbide, we know, and it's already happening, that the switching frequencies will go up. In order to really prove this point and give you a better feeling on the type of performance that we are talking about with C2000 microcontrollers, we did develop some benchmarks which are publicly available on TIA.com. And for developers doing real-time control algorithm, what is really important is the time between the moment where you sample, for example, your current and your voltage, and the moment you take a new decision to drive your PWM outputs. And here we decompose into different steps: the ADC interrupt response, the context save, reading the ADC registers, the control algorithm, obviously, but also writing back to those PWM outputs. All those different steps contribute to the performance of a real-time system. And by design, the C2000 has been optimized to keep this time as small as possible. And for example, to give you an element of comparison, a typical Cortex M7 device would need to run at 200 megahertz to achieve the same latency of C2000 running at 100 megahertz. So essentially, the architecture is 2 times more efficient than the Cortex M7 when it comes to real-time control algorithm. So with this in mind, let's have a look at what we are introducing today. It's a new member of the family, the F28P65X, that comes in the mid-range with 3 core, offering a processing power of up to 600 MIPS and giving you up to 1.2 megabyte of flash. Some of the key points that we will develop are really on the PWM and analog innovation, and the fact that we are able to simplify software, simplify the hardware implementation to bring further level of integration and giving you an additional option to reduce your overall system cost. It's a highly connected device, and we will drill further, looking at the different options, different package options, together with more features to make your safety implementation easier, and also your security implementation easier as well for both industrial and automotive. So if you put the device in the context of the overall platform, you can see that this diagram is describing on the x-axis the different packages, and on the y-axis the different memory size. And the F28P65X is basically an addition to the platform, and that brings overall software compatibility across the different devices, moving from the low end to the high end. And in some cases, the devices are also pin-to-pin compatible. Looking at the application, again, we can highlight two domains. One is motor control, another one is digital power. And the F28P65X, for example, is a great addition to the family to implement size-constrained multi-axis robotics, where you would have to implement on the same device control of multi-axis plus EtherCAT plus communication plus safety and security all onto one single device. So you can think about a dual-axis servo drive, or you can think about a robot servo drive, encoders, surgical robots, so those kind of applications. And then on the digital power side, we can highlight, for example, when it comes to solar system or EV charging, the need to achieve higher power level, and that typically comes with a new power architecture. And in the future, power supply will become more complex, and the F28P65 is enabling developers to implement those architecture in a more simpler way. And another example we'll discuss as well in our automotive side, the F28P65 is enabling designers to implement a single chip onboard charger plus DC-DC with one single device. So let's have a look at the block diagram of the device. There are many functions to look at, but like for any other control application, the first step is to look at the samples, the information that we collect with the analog. So on the analog side, we have an A2D converter, which is 12 or 16 bits, coming with 3 ADC module, enabling you to sample 3 channels at the same time. And we have up to 40 channels available. What is really interesting and the new features is the hardware oversampling combined with a new compare unit that will enable you to implement the next generation of control, like peak current mode control with an extra low latency, for example. So let's drill further and have a look at one of the features for the ADC, which is really the oversampling function. So oversampling is a well-known technique that enables to achieve a higher effective number of bits. And this can be done traditionally by using software implementation with multiple start of conversion involving the CPU to make some calculation and to treat in real time the different samples which are captured by the ADC. On the F28P65X, we introduce some new features, which is basically hardware oversampling. And with different scheme up to 128 oversampling, period averaging, precise trigger positioning, you can see here the new features on this ADC. And the immediate impact is really a simplification and the code optimization for the software developer, where within a single start of conversion, combining the post-processing, which will make for you hardware accumulation and averaging, you have really a zero software overhead that will come with these new ADC features, giving you in this benchmark up to close to 40% improvement in CPU cycle and code cycle. So if you look more in details into the different new features, a couple of things that needs to be highlighted: the trigger repeater that really can generate up to 128 samples in a single trigger. Those triggers can be spread according to registers, and we'll see two examples in the next two slides. And a very powerful post-processing block that contains a 24-bit hardware accumulator, shift function, a dedicated oversampling, interrupt signal, min-max sample calculation. So a lot of new registers to calculate and manipulate those data on the fly while the ADC is running. And many of the registers are shadowed, enabling to really change the configuration on the fly. So taking one example of an oversampling, here you have an example of a timer counting up and down, and we trigger on the rising edge of PWM1 a starter conversion for the ADC. And here in this example, we choose an oversampling mode where we have a burst of conversion with 4 signals, and we define this with the right registers. But we could have a different approach where, for example, we could decide to evenly spread the oversampling within the state of the PWM using registers. So you can imagine that in the future, as the PWM frequency are increasing, you don't need to use extra overhead for software to really synchronize and plan your starter conversion. This can be done in a very simple way using the registers. And this is what this slide is kind of showing here, where on the left, we have a variable frequency PWM, and you have the associated PWM output here that is coming for this graph. And we could imagine that for this example of variable frequency converter, you would want to trigger starter conversion at those different events. And typically, without the flexibility of starter conversion I just described, maybe you will use one timer to generate a starter conversion for trigger number 1, another compare value to start conversion number 2, and then you will need to use an additional PWM and another timer to trigger number 3, and so on. With the new hardware ADC implementation, you have much more flexibility in terms of the starter conversion, and you can synchronize your starter conversion with the different PWM period, even if the PWM frequency is changing. And this will enable designers to really decide to trigger your starter conversion at places inside the PWM period where they know the noise, the switching noise, for example, can be avoided. So it brings more flexibility, simplifies the software, and in particular for the future, if you think about those increasing switching frequency, which are also changing on the fly, a much more flexible ADC management. Once we did collect those ADC inputs, the next step is really to treat the information, to make some calculation and some processing. So the device is offering 3 cores running at 200 megahertz each. We have 2 DSP core, which are floating point 64 bits running independently. And one of those DSP core is also coming with a lockstep function, meaning that there is another core running in the background that is continuously verifying the integrity of a set of registers. And that brings a lot of flexibility and simplification when it comes to safety implementation and safety certification. And then there is a third core, which is a control law accelerator floating point unit running at 200 megahertz. So really 3 core running independently that can run different control algorithms. So if we zoom into some of those processing functions, let's have a look, for example, at the control law accelerator, the CLA, which is really optimized to implement time-critical control loop. It can access the registers independently of the different CPUs, and it is really defined to implement intensive math computation. And the key point is minimum latency, So if you imagine like a 2-pole 2-0 controller, we are giving you here the benchmark, showing you the improvement in terms of cycle, and also a list of the different MATLAB function that you can use using this floating point core. In addition, to improve the overall efficiency and minimize latency and save cycle, the device contains some mathematical improvement like the trigonometric math unit, or the TMU, which is optimized to implement some sine and cosine functions. So if you think about a motor control function or a space vector calculation, you will need to calculate some Park function, Clark transform that involve a lot of sinus and cosinus. And using the TMU, you can have up to 85% improvements in terms of cycle. So we talked about the sensing, the processing. Now let's have a look at the actuation, the PWM unit, which is really one of the key innovation and highlights on this device. We are providing more PWM up to 36, all high resolution, 150 picosecond. And the new generation of PWM that we call Type 5 is enabling new function to implement the control of the future of what we see as being the future of power electronics, like matrix converter, multi-level converter, resonant mode converter. And I will talk in a second about the new function inside those PWM units. So the new features on the PWM unit comes in different subsections, and I will develop the ability to build more complex waveform, and also our new illegal combo that implement new flexible way to implement deadbands, and highlight one example also of the new digital compare using the capture unit. So we are really talking here about more flexibility and the ability to simplify the overall hardware design and also simplify the software. So let's have a look at that. So essentially, what is really new inside this PWM new block is that all the different PWM modules now can be synchronized to each other. And when we zoom into one particular module, we can generate up to 4 pulses within one PWM period. So this brings the benefit to generate more complex waveform without the need to implement special code or to add external logic. And this is particularly useful for high frequency resonant topologies. So we can see here on those block diagram that we have 8 compare value per timer, a different set of shadow registers, and you can also implement 4 compare value for 2 complementary PWM like compare A and compare B. So if you look at one typical implementation, you can see here on this diagram that the PWM A is using compare A 2, 1, 2, 3, and 4, B 5, 6, 7, and 8. And we are able to generate this waveform and to reload using the shadow registers different either action qualifier or even changing the value of the compare. So fundamentally, if you look at this signal, there is the complexity comes with the fact that in the future, as the PWM frequency are increasing, you will not need to play with different software tricks to implement those functions. Basically, PWM A and B can be totally independent, and you can program in software in a very precise and deterministic way using specific registers the value of compare 1, 2, up to 8, and maintain a very stable and precise PWM pattern, even though the frequency is increasing. So we are bringing more flexibility on the software implementation when the PWM frequency will increase. So it will consume also less resources from the CPU cycle. Another function which is very important is the ability to make a safe turn on and turn off on the PWM. When, for example, you implement a 3-phase, 3-level ANPC power supply, one of the key functions and key challenge is to turn on and turn off the PWM signal at the right time. And the F28P65X is implementing a new feature, which is a minimum deadband logic and illegal combo logic module that will bring more a simplified implementation on hardware and software to safely turn on and turn off a power supply and or avoid shortcuts on the power supply. And also that will help to prevent unwanted output combination on the PWM outputs. So additional registers have been added, like a functional deadband block that will prevent the generation of one signal if a combination occurs. And this is backed up with a logic table that will define what are the illegal combinations. So, for example, here we have two signals PWM A and B, where we define a minimum delay between those falling edge and rising edge of respectively A and B. So this can be programmed. And the new illegal combo logic defines a lookup table that will basically define the truth table of what is acceptable, what is authorized or not. And again, as you imagine in the future, PWM frequency increasing or power supply architecture becoming more complex, normally to implement that, you need an external logic, FPGA or CPLD, plus some software manipulation. Here we are giving you an opportunity to simplify your software, remove external logic to simplify your software and reduce your overall system cost. Another function that I'm highlighting today is the ability to detect a missing edge event inside a configured time window. So here, for example, using the capture unit, we can decide to generate a trip or an interrupt if an edge is not detected within the time window that I can program, defining the min and max value. So this brings additional safety options, more flexibility to implement your power supply and to implement a safety strategy at the system level. So at this stage, we talked about the ADC, we talked about the processing unit, and we talked about the PWM. So let's take an example for looking at an onboard charger integration. So on the left here, you have a typical onboard charger that comes with two main blocks. One is a power factor correction, and another one is a DC-DC converter. And typically, we can see that there is a microcontroller to control the PFC, one to control the DC-DC. And of course, there is a host MCU somewhere. If we look at optimizing the cost, integrating further, there is an opportunity to, using the F28P65X to implement a single chip implementation of onboard charger plus onboard charger using PFC and DC-DC control with one single device. So if you look at the block diagram of the power supply here, you can see a power topology, which is in this case up to 22 kilowatts, three-phase. It is composed of two-phase totem pole per phase and also two LLC stage. So if you look at the power state requirements and if we list the different signal and input-output which are required in terms of PWM, ADC comparators, the F28P65 has the right hardware resources to go and control this power supply. But that's only the hardware portion. What is really interesting as well is that designers also have the opportunity to allocate the different control loops and coming with different frequencies across the various cores. So for example, we could implement the power factor correction with a CPU1 and the two LLC using, for example, the CLA. And typically, the totem pole PFC comes with a fixed frequency while the frequency of the DC-DC is changing. So you can separate those different control loops on each CPU that makes the software more robust and simpler to implement. And here you can imagine, a housekeeping function running on the third CPU. Interestingly enough as well, there is an opportunity to allocate the ADC, the PWM, the resources across the different CPU. And those improvements that I described on the ADC and the PWM will help designers to implement a more precise overcurrent or overvoltage protection, for example. And that will give you an opportunity to optimize the need for external logic or external components, and therefore reducing the need for external monitor on the output voltage or output power to implement a safety function. So really the key point with this example that could be extrapolated to a charging station or another digital power application like solar, is that designer can implement now self-control in hardware as opposed to a more complicated software integration as previously implemented. So innovation on the ADC, innovation on the PWM that enables to integrate more, remove external logic, and distributed resources with 3 different CPU that makes the software implementation simpler and also more robust. So now if you look back again at our block diagram, we can see that there are many other things that we could highlight. For example, on the connectivity side, a lot of different interfaces with the CAN, CAN-FD, USB, high-speed serial port, and also the EtherCAT port, which is very popular for robotics. And this EtherCAT port comes together with a new package, a very small one, 9 by 9 millimeter, that brings basically this opportunity to provide great control, safety, security, communication into a very small package for those space-constrained applications. Additional function and features have been implemented to implement easier safety, depending on your safety requirements. And the memory architecture as well has been improved, allowing designers to really support multiple bank with different size to different CPUs. So you can really allocate your memory resources in a very flexible way across the different CPUs. So here, for example, this is a block diagram of the P65X used as a single chip servo drive plus EtherCAT, and the device provides a system on a chip with a control, communication, safety, and security. And we do provide, for example, for EtherCAT training libraries and resources for you to get started on this communication protocol. So that brings us to basically on how to get started. And one great starting point is to really look at our developer zone at dev.kia.com, where very quickly you have the ability to select your device, connect to our low-cost board like the Launchpad, and try the example by either downloading them on your computer or even trying directly example in the cloud to immediately get a flavor on how to use the ADC, how to use the PWM, how to use the CPU. And many of the examples are coming with, we have examples on each of the peripheral using our new tool called sysconfig that enables to graphically configure, for example, the ADC input and outputs. You can add additional libraries. The C2000 software ecosystems come with many mathematical libraries. I did highlight the sinus, the cosinus, but we have much more in terms of FFT, signal processing. And you can, for free, download all this software and environments inside the debugger, which is called Code Composer Studio, and in order to start your project. And if you are new to the digital processing, to the world of real-time control, we have a lot of libraries which are fitting into what we call the C2000 Academy. It comes with 24 hours accessible exercise on ADC, PWM, communication, with quiz and videos and a lot of things to learn quickly at your own pace, the benefits of a real-time microcontroller. One key highlight also is when you start to develop on C2000, as I explained at the beginning, it's not only one device, it's a platform of devices which are software compatible, sometimes pin-to-pin compatible. So imagine you will start today a project on the F28P65, leveraging our existing tool like the sysconfig and libraries. Tomorrow, when you decide that, hey, I have another project that needs a lower end device or maybe a higher end device, the tool will identify for you what are the changes and potential conflict in terms of registers, pins that don't exist between two devices to migrate across the devices very easily. And really, it's an environment that provides a one-click migration, addressing for you all the changes that needs to be done in the software, moving from one device to another. So one project can be really migrated across different member of the C2000 family, making your software investments very flexible in the future. So in terms of resources, here is a cheat sheet for you on how you can get started. Again, the F28P65X is available on Kia.com. It is sampling. It is moving in production by end of this year. And we provide product page, technical blog, product brief, a lot of training for you to get started, plus all the libraries to implement, configure the registers, but also the motor control library, digital power library, and coming with our sysconfig tool for graphical implementation, the one-click setup I just talked about, and backed up with some cost-optimized, low-cost control board, like, for example, the P65 Launchpad. So this concludes the presentation for today. Today, we discussed about the new addition of the C2000 real-time microcontroller, the F28P65X, that brings new capabilities to implement the next generation of power electronics for the future with a new PWM unit that makes the software much simpler to implement, that enables to reduce the need for external components and reducing system cost. The new EDC features, again, simplifying software and allowing developers to start conversion at any time inside the PWM cycle. A lot of great level of integration with EtherCAT into very small package, 9x9mm with flash plus safety plus security, contributing overall with this overall system cost reduction. So if you want to get started and know more, I invite you to look at on the website at kia.com/2000 to get started and to get more information. And with that, I thank you for your attention and looking forward to supporting you on your project. Thank you.